So next up will be Frank. He's a PhD student at University of Michigan, Ann Arbor, currently working as a research assistant for Ford Center for Autonomous Vehicles, advised by Katie Skinner. His research focused on robot perception and state estimation. Can you share screen, Frank?
I think he has some technical issue. You can keep talking.
Okay. I hope everyone has a great day.
Yeah, hello everyone. My name is Frank. So I'm a PhD student, a fourth year PhD student in University of Michigan. And yeah, sorry I cannot be there in person due to some visa issue. But today I'm going to present like multi-model high fidelity scene reconstruction and data synthesis for robot scene understanding. So yeah, robot autonomy is an important task in robotics, and it's composed by perception, planning, and also action. And nowadays, those components are usually done by learning-based approach, like learning-based detection, segmentation, learning-based forecasting, path planning, and recently, like the VOA. After the VOA came out, we also found learning-based approach can directly output the action signal. So one of the famous learning-based system for autonomy is the Tesla FSD system, showing like really promising result on the road. And in US, people can use it, use the beta version to drive on the road right now. And they even have a robot taxi in Texas showing promising result. And the other application is the robot manipulation, like recent VOA showing like learning-based approach can do really good robot manipulation that robot cannot do before. However, this kind of learning-based approach have their limitation. So first, I take a look at the autonomous driving failure case. So this is a video done by a YouTuber testing the Tesla FSD system. I think this is a video captured like only a month ago, and they are testing a latest FSD system. So basically here you can see there is a like a random obstacle on the highway. So it seems like a really simple simple scenario because there is something in the highway, and people will definitely know they should break in this case. But because this is an unseen obstacle, which is really rare in the training data, so the Tesla car failed to recognize it and then it just crashed into it. And this can cause like a really bad accident. And here's another example of the Waymo car driving into flood. So again, this is also a rare scenario that they don't have too much this kind of scenario in the training data. So the Waymo car just gets stuck in the flood and fail to handle this kind of case. And here is another example in San Francisco that during the power outage, the traffic light is not working and the Waymo car just gets stuck. So again, this is like a long tail case that we only have lake data for the autonomous driving training. So the challenge of current learning-based robot autonomy is that it fail on rare scenario due to insufficient corner case training data. And the data bottleneck also happened to robot manipulation. So for example, here is a video from I think Pi0, and they are showing some failure case of like stacking balls and also put something into microwave. So it seems like a really easy case for human, but it become a challenge case for robot. And the main reason is because it is really hard to collect data for this kind of robot policy training. So yeah, real world, especially for robot manipulation, it will require like real world interaction between the robot and real world object. So they usually only use like really few sequence for training, which cause insufficient training data, and so that the robot can fail in even simple task. So yeah, to solve the data bottleneck, the really common way right now is to do data synthesis with high fidelity reconstruction like nerve and Gaussian spotting, as previous keynote speaker talked about, like generating digital twin using nerve and Gaussian spotting, and then we can do novel view synthesis inside the scene. So here's a video from NVIDIA showing the nerve reconstruction of the driving scene. And then after the reconstruction, they can like do scene modification, like removing all the moving object and also do novel view rendering. So we don't have to change the sensor setup or like changing behavior or recollect data because we can just like generate more data using our digital twin. And here is another video showing like uh, present in CVPR 2024. So on the top, you can see the original video, which is just a really normal driving sequence, which is really bored. But after the nerve and Gaussian spotting reconstruction, we can change it into a safety critical scenario that is really rare in real world data collection. But it's really important to teach the robot to handle this severe condition. And yeah, nerve and Gaussian spotting for data generation is also used in robot manipulation tasks. So for example, here I'm showing like robot Gaussian spotting and they can do like really realistic image synthesize. They can synthesize really realistic robot image that is really similar to the real world data so that we can generate this kind of data without using a real robot. So it can definitely help the data collection. However, nerve and Gaussian spotting is originally designed for camera only, but in robotics, we usually have like more sensor than camera. So for example, for car company, autonomous driving company like Waymo, Motional,
Sorry to
Zoox.
interrupt, Frank. You have
Yep.
5 minutes more. Maybe skip some of the introduction.
Oh,
Yeah,
okay,
five
sure.
minutes more. Yeah.
So yeah, basically they have like more sensor. Um, yeah. So basically in robotics, we use different sensor modality to improve perception robustness. So, but the nerve and Gaussian spotting can only support camera. So the motivation of my work is to make sure the Gaussian spotting and nerve can support different sensor modality. So the first one I'm going to talk about is called LoNer. It's a LiDAR nerve-based SLAM. So we basically extend a nerve to support LiDAR, and we also extend it to SLAM. So here on the right-hand side, we show like really dense reconstruction using like sparse point cloud-based LiDAR sensor. And yeah, so the motivation of this work is that the traditional LiDAR SLAM can only provide a sparse point cloud shown here. So it is not a really good presentation if we want to have a digital twin or we want to generate like novel data. So it's a sparse representation, and on the right-hand side, we show that using the nerve because the continuous property of the MLP, we can generate like really high fidelity geometry. So yeah, here is the result of our loaner result and comparing with all the existing depth supervised nerve method. And we show that our method provide the most accurate geometry. Yeah. And next word I want to talk about is the RGBD Gaussian spotting. So in robot manipulation tasks, we usually have a lot of like, we should use RGBD sensor because it's like near range and indoor scenario. But yeah, so here I'm trying to use the depth information from the depth camera correctly. So here on the top, you can see the original Gaussian spotting only use depth information to initialize Gaussian. So when we do novel view rendering from like extreme view, you can see the geometry is basically wrong and the novel view rendering quality is really bad. And at the bottom here, I show our proposed ZGS, which is correctly using the depth information for supervision. So you can see when we are doing novel view synthesis, the image looks much more realistic. So yeah, quickly comparing our work and the proposed method and our work and related work. So existing depth supervision only try to align the mean of the Gaussian to the measured depth. So when you render from novel view, the geometry will look wrong like this one and the center loss using other paper. So yeah, basically the Gaussian shape is misalignment can cause like really bad novel view synthesis. And on the other hand, our depth supervision try to make sure the Gaussian shape is aligned with the measured depth. So by doing this, we show that the novel view rendering quality will be much more better. So here's a novel view rendering comparison of our method and all the baseline, and we show that our method is really robust to view change when we are doing this novel view synthesis. And here's another example showing that our method can use just one single image captured from iPhone, using the RGBD data captured from iPhone to do really robust face reconstruction. So here on the left-hand side, you can see the traditional, like a classical depth supervised method for Gaussian spotting, and the shape of the human is inaccurate, so which caused the novel view rendering quality to become really noisy. And our method is really robust to view change because the correct geometry reconstruction. And yeah, so we also extend this idea from RGBD camera to using LiDAR. So it's also using depth information, but we are using LiDAR on the autonomous driving car. So here on the top, you can see our baseline, which is street Gaussian. They're also using LiDAR depth information as input, but they're not using it in a correct way. So by doing correct depth supervision, we show that our method can provide much more accurate reconstruction on the moving actor, like the red vehicle shown here. So here I provide some video showing the comparison between baseline and our method. And we show that doing correct depth supervision is really important because it can help us to reconstruct the dynamic object inside the scene that we only have like limited view, like limit observation. So you can see that our actor reconstruction is much more better than the baseline. Okay, I'll quickly go through this. So the next paper is called radar spot. So we have talked about like using RGBD and also using LiDAR for Gaussian spotting. And here I want to extend the Gaussian spotting to radar sensor modality because a lot of autonomous driving vehicle, they are using radar as the input. So here radar spot is about like radar Gaussian spotting. And here we show that our radar 3D reconstruction can be really accurate and really similar to the reference LiDAR ground truth geometry. So the motivation of this is that radar is more robust to weather conditions, like during raining and fog condition, camera can be blurry and LiDAR can have like a lot of like noise particle inside the data. On the other hand, radar is super robust to this kind of adverse weather condition. So you can see radar can still observe the vehicle in front of us, even though it is really foggy in the radar in the camera image. So yeah, so radar can enable sensing beyond human perception, which I think is important in the future. And here I show our radar Gaussian spotting novel view synthesis comparison between our method and the existing baseline. So on the left-hand side,
Sorry to
uh,
interrupt, Frank. We need
yep,
to wrap up.
yep, okay. So yeah, basically we're doing novel view synthesis, comparing with existing baseline. We show like we have the best novel view synthesis quality. And we show this kind of method can also work in extreme weather condition. So yeah, thank you. Uh, yeah, I guess we can do the QA section offline, but
Yeah.
okay.